Good morning this Monday morning. It's time to start on problem 9. And what have we got? F of z has period 1, which is very nice and satisfies this relation. All right, and we must show that this holds for all gamma and gamma naught of 4. This reminds me very much of proposition 30, where we're working on the capital theta function. We need to find the generators of gamma naught 4. I prepared that, and you've seen it before. I've corrected it a little. The group is generated by minus the identity t and then this guy, which we will call alpha. So basically we need to show that operating with alpha that f is stable by that. They say k is even, that means it holds for minus unity. So it's minus 1 to kth times f. And since this should be equal, since k is even, this is equal to f. And that means we just need to show this guy, and then we are done. And what we know is the relation given in the problem, which we must formulate by some matrix, and the obvious matrix is, and I have defined alpha here, so let's call it beta minus 1, 4. It has determinant 4. And that means that f of z beta k equals the determinant to minus k halves times 4z to kth. And now we must use the relation, of course, and reduce it slightly. 4 to minus k halves and 4 to minus k halves, they cancel. So we have 4 to kth. What's the point of this? Well, 4 to kth and minus z squared to k halves f of z Now what is this? 4 z to k. No, it's minus k. My God. Silly, silly, silly. So here we have z to kth and z to minus kth. We'll just have to redo this totally. A cancel pen. This cancels, and z to minus k and z squared to k halves cancel, meaning we are left with 4 to minus k times minus 1 to k halves. We'll look at that, see if we need any reduction there. So that's beta. And then we must check how we can find alpha from beta. Maybe we can use the formula from the proof of proposition 13. I'm thinking about formula 330. Oh, it's actually the same guy they have. S to t fourth I'll just copy it. I'll just show you the page so you can see it. So of course we have the case n equals 4, and then s t to fourth s equals, and we can of course use this one as a generator as well. So we'll just check what it looks like. Oh, I had it here. So it's minus 4, 1, 1, minus 4z. That makes a slight difference. So I'll just write up what we need to show. So what do we do? What do we do? Well, we just operate with beta t beta on it. T and then beta. Beta I already did compute. And t, that's easy. And now it's time to use this one once more. So it's f of beta z evaluated at z plus 1. I think I did something terribly wrong here. We have to show that it's just equal to f of z. Well, let's go on with the show. So it's the same once again. And f of z plus 1, that equals f of z, of course. So we get 2 to minus 4k and minus 1 to k. Since k is even, that gives unity. We're close. Go back to the dream world. We need to show that it's just equal to f of z. And I'm just wrong by this factor. I have no idea how that cancels out, which means it's time for a break. I have looked it over and found various mistakes, a little one here. And then this should be plus. It's the determinant to k halves, and the determinant is 4. So it's 4 to k halves. What I'll do, I'll just delete it and then do it again. All right. So first the determinant to k halves. Next, it's 4z to minus kth. Then we use the transformation formula to get this. And 4 to k halves times 4 to k halves, that's like 4 to kth. Oops, here we have 4 to minus k, so they cancel. So 4 to minus kth and 4 to kth, all right. Then we have z to minus k, and we have z to k here. So we are left with minus to k halves f of z. That makes stuff much simpler. Minus to k halves. Then we apply t, and then we apply beta, and reduce. And we are finally home.